So multiprotic acids means that you're dealing with acids with multiple protons, in other words, hydrogen. Taking phosphoric acid as an example, because we have 3 protons, we have 3 different pKa values. 3 to 2 gets us pKa1, 2 to 1 gets us pKa2, and 1 proton down to 0 gets us pKa3.
So let's do a problem. Determine the ratio of HPO4 to H2PO4 needed to create a pH of 7.4. And then for H3PO4, we're given the Ka values. So we know we are dealing with 2 hydrogens going to 1. Since we are given the Ka values for H3PO4, first Ka goes from 3 hydrogens to 2. So that's not it. And the next one deals with 2 hydrogens to 1. So this will be the Ka we want. We know we'll be using the Henderson-Hasselbalch equation, so let's convert this to its pKa, which gets us this value. Next, we'll write out our HH equation. We know our pH is 7.4, pKa was found to be 7.2, but now we're just going to treat A- over HA together as one variable, which we'll call x. From here, we'll solve for it. Use base 10 to cancel out the log, which gets us 1.58. So we know x is equivalent to A- over HA. If we convert this fraction to a ratio, the numerator is left of the colon, while denominator is on the right. Next, we know our A- is our HPO4 and our HA is H2PO4. This matches the order the problem asks us, and the final step is to write the right side of the equation as a ratio, in which all you need to do is add a 1. Before we move on, let's say the question didn't ask for this order and instead flipped the order. In this case, we would flip the ratio, and we'll do the same thing on the other side. So this would be our answer. In case you don't see this in a multiple choice option, this is another way to write the ratio. The 0.63 comes from dividing 1 by 1.58, so keep that in mind.
So some problems will ask you to find the proper buffer. In other words, you'll be given a pH value and you have to find the appropriate pKa to correspond with it. In these situations, take the pKa values, create a plus or minus 1 plot for each of the pKa values, and find the pKa range that corresponds to the pH. That's the pKa to be using. Before we move on to the next portion, if you haven't liked the video or subscribed to the channel yet, please do so.
Also join me at nicoscience.com. Here you can find my tutoring website where you can book a session in this button below and choose from a range of subjects from biochemistry, physiology, biology, chemistry, and genetics.
Alright, back to the video.
H3PO4 is placed in a solution where the pH is 11.5. Given 0.02 molars, find concentrations of the predominant acid and conjugate base forms. And we're given the pKa values. We start off with a pH of 11.5. So now let's take the plus and minus 1 ranges of each of the pKa's. So for the first one, minus 1 gets us this, and plus 1 gets us this. 11.5 falls nowhere in this range, so that's not it. Next one gives us this range, not it either. And the last one gives us this. And take note that this is the third pKa, so we know we're dealing with the last proton of H3PO4 going down to no protons. Next, write out the HH equation where we know pH is 11.5, pKa is 12.38, and for log, we'll set that as x. From here, solve for x. Take the base 10 to cancel out log, which gets us 0.132. So we can rewrite x back to the fraction, and to find the concentration of A- and HA, here we need to feed in a second equation. The first one we solve for, we can call our ratio equation, and the second one, which we'll put in just a bit, is our total equation. We can get this from the problem where it tells us that we have a total of 0.02 molars. In other words, our acid and conjugate base forms added together equal to this 0.02. And now we'll rewrite this second equation to solve for A-. All we'll do is multiply HA on both sides, which gets us this. And now we'll insert this value for our A- in our second equation. From here, we'll add these HAs together and solve for HA. Now, what is our A minus? Well, let's rewrite the second equation we had. All we have to do is insert the HA here, which gets us this value for our A minus. Finally, we know our HA is HPO4, and our A minus with one less hydrogen is our PO4. And don't forget the units.
As a review of the pH series, let's do a recap on what equations to use for which types of problems. If you're just asked about a strong acid in a problem, all you'll be using is the pH equation, where the HA is the strong acid. For the strong bases, you'll be using the POH equation, and just know that there's an equation for you to interconvert between the pH and POH. Weak acids, you'll be using one of two equations. The first one that you should be going to is the Henderson-Hasselbalch equation. But if you find yourself not being able to get the pH or pKa from the problem, then you should resort to the Ka equation. So that's it for this video. In the next one, we'll be talking about strong acids and bases as they're mixed with buffer solutions.